Welcome back to Statistical Methods. This is week 4, lecture 2, where I will be covering the second installment of the unit on hypothesis testing. Now, homework 2 is due on Monday, September 21st before class. And this covers z-scores on the standard normal distribution. And quiz 1 is due this Friday, September 18th at midnight. I will note that for homework 2, this can be in by midnight. Now, last class we covered the basic logic underlying null hypothesis significance testing, or NHST, which is the predominant framework used by social scientists to test their research hypotheses. And here's the logic below. If what we actually observed in our data would have been highly improbable to occur if the null hypothesis, or the hypothesis that there is no relationship between the variables of interest, were true, we reject that null hypothesis and take our result as evidence in favor of the alternative research hypothesis, or the hypothesis that there is some kind of relationship between the variables of interest. So I'm going to go back through the vitamin example to put these concepts into practice again and to provide some review. So a research team has developed a new vitamin that they claim speeds up the development of babies and allows them to walk at an earlier age than most babies. Thus, we have our hypothesis: the vitamin will make babies walk at an earlier age than babies in the general population who have not received this vitamin. And we will rely on an artificial example using z-scores with a sample mean of n equals 1, so just one baby in the experiment, to get these general principles down, and then later extend these logic to larger samples in the following unit. So imagine we know that for the general population of non-vitamin babies, the mean age when they start to walk is 14 months, with a standard deviation of 3 months, right? So again, our mu, or the population mean, is 14, and the standard deviation, sigma, as noted in the population level, is 3. Now let's imagine this distribution of walking ages follows a normal distribution and looks like this. Now, what does the null distribution look like in this case? In other words, what would a hypothetical vitamin baby distribution look like if the vitamin had no effect? And we know now that this would look exactly like the general population of babies who have not received the vitamin. Right? Because if the vitamin had no effect, there'd be no difference from that population distribution of walking ages. And the mean would be 14, and the standard deviation would be 3. So with this in mind, we conduct our experiment, administering the vitamin to a single baby, so a sample of n equals 1. And this baby receives the experimental vitamin and begins walking at the age of 8 months, so x equals 8. Clearly, this is quite a bit earlier than most babies, but is it different enough to say that the vitamin worked? Well, this is where NHST and probabilistic thinking enters the picture. So the process, again, is we convert our vitamin baby's walking age, x, into a z-score to see how extreme it is with reference to the overall non-vitamin distribution. So again, we subtract the mean from our score and divide by the standard deviation, which yields -2. So that is our z-score for this vitamin baby. And now we can use the standard normal distribution to ask how improbable it would be to see a baby walk this early if this baby were sampled from the null distribution. So that would mean that the vitamin had no effect. So we use the Shiny app, and we select a one-tailed lower distribution. Because we want a particularly small number of months here in order for this vitamin to work. And we enter our x-axis quantile in the number entry box of -2. So that's where we enter our z-score. And it returns a probability of 0.02. So that is the probability of finding a result as extreme as the one that we did. So a z-score of -2. assuming that this vitamin doesn't work. So there is only a 2% chance that we would find a result as extreme as this, so a walking age as early as this, if the vitamin really had no effect. So is it improbable or extreme enough to reject the null hypothesis that the vitamin had no effect? Because the standard convention in the social sciences is p is less than 0.05. That is, if there is a lower than 5% chance of finding a result as extreme as the one we did, if that null is true, we take this as evidence in favor of the research hypothesis. So in this case, that the vitamin worked. Or in other words, we can reject the null hypothesis that it didn't work. So the probability of obtaining a result as or more extreme as the one we found, assuming the null is true, is called the p-value. So the p equals less than 0.05 criterion is currently the gold standard used by social scientists to determine whether we can conclude that the research hypothesis was supported or not. For example, whether we can say two groups' means were different from each other, whether we can say that two variables are correlated, or whether or not an intervention or treatment worked. As was the case with the vitamin baby, we saw that this treatment or the vitamin worked at yielding an earlier walking age for this particular baby. Now the cutoff p-value is decided upon in advance of conducting an experiment. So that means setting it at 0.05 is determined before actually collecting data. This number also goes by the name of the significance level. So we would say that most social science experiments use a significance level of 0.05. In some cases, researchers want to be more conservative than this, requiring a more extreme or improbable result in order to reject the null hypothesis. So they will use a lower significance level, for example, 0.01 or 0.001. So that's a 1% probability or a 1 in 1,000 probability. Now, p-values vary as a function of two things: effect size, which we'll talk about later, and sample size, the number of participants or observations. Now, these factors share negative relationships with p-values. That means as effect size increases, the p-value decreases. And as sample size increases, the p-value decreases. And we'll discuss this fact and why it can pose certain issues more at a later date. So when a p-value in an experiment is lower than the predetermined significance level, which is usually set at 0.05 prior to collecting data, we say that our result was statistically significant. Thus, a statistically significant result essentially means that we found evidence for some kind of effect, or evidence for our research hypothesis. So let's review the terminology we've covered so far. An effect is a relationship, either causal or correlational, between particular variables of interest. A hypothesis is a prediction made about the existence of an effect. A research hypothesis, in most cases, is the prediction that there is an effect of some kind. A null hypothesis is the prediction that there is no effect or no such relationship. The p-value is the probability of finding a result at least as extreme as the one we found, assuming the null hypothesis is true. And the significance level, also called the p-value cutoff, is the level of improbability that must be reached in order to reject that null hypothesis, and to say that the research hypothesis was supported. Statistical significance is the term used when the observed p-value is lower than the significance level. And NHST is null hypothesis significance testing, or the inferential statistical framework, incorporating all of these terms. So we'll spend much time later during the semester learning about how NHST works in various research contexts. So with numbers of conditions, with different types of variables. And the core logic here will remain the same, but with different types of experiments come different types of statistics and different types of probability distributions. So the textbook introduces a systematic approach to NHST involving 5 steps. And we'll now walk through each one of those steps in detail, then see how they'll work in practice. So step 1 is to state your research question in terms of the null and research hypotheses about populations. Step 2, determine the characteristics of your comparison distribution. Step 3, determine the cutoff score from the comparison distribution for rejecting the null hypothesis. Step 4, determine your sample score on the comparison distribution. And step 5, decide whether to reject the null hypothesis. So for the research question we had earlier, does vitamin X make babies walk earlier? In step 1, we have to state our research question as null and research hypotheses. So keep in mind our 2 hypothetical populations of interest here: the vitamin distribution, or the distribution in which babies receive vitamins, whose mean will be denoted as mu1 or mean 1, and the no vitamin null distribution, whose mean is mu2. So this is the distribution of babies that do not receive the vitamin. So it has its own mean, and the vitamin distribution will have its own mean. Now, our research hypothesis is that babies who get vitamin X will walk sooner than babies who do not. So in terms of our population parameters, mu1, so the mu of that, or mean of that vitamin babies distribution, should be less than the mean of mu2, or the distribution in which babies did not receive the vitamin. It should be less because we're looking for an earlier walking age for the distribution in which babies received vitamins. So this is saying the walking age population mean for babies who get the vitamin is lower than the walking age mean for babies who do not get the vitamin. In simpler terms, babies who get the vitamin tend to walk earlier than those who don't. That's our research hypothesis. And this is what it would visually look like. So again, our research hypothesis is mu1 is less than mu2. So here is our vitamin distribution. So the distribution of babies who receive the vitamin. And notice that their walking age is earlier, mean equals 11, and a standard deviation of 3. And here is the null distribution, so the distribution of babies who did not receive the vitamin. And notice their mean walking age is higher at 14 months with a standard deviation of 3. So this is a visual representation of our research hypothesis, that the vitamin distribution will have a lower mean than the null distribution. Now, the null hypothesis, on the other hand, is the hypothesis that there is no relationship between the independent variable, which in this case is taking a vitamin or not, and the dependent variable, or what we measure, walking age. Thus, the null states that the vitamin has no effect on walking age, and the 2 population means look exactly the same. So in terms of population parameters, mean 1 equals mean 2. So the walking age population mean for babies who get the vitamin is the same as the walking age population mean for babies who do not get the vitamin. In simpler terms, babies who get the vitamin do not learn to walk sooner than those who do not get the vitamin. So here's a visual representation. So under the null hypothesis, mean 1 in the distribution of babies who receive the vitamin is equivalent to mean 2. So the mean of walking age for babies who did not receive the vitamin. And you can see that, yeah. So this vitamin distribution under the null hypothesis would have a mean of 14, as would the null distribution. So the null hypothesis is that when babies receive the vitamin, their distribution looks exactly the same as babies who did not receive the vitamin. Step 2 is to determine the characteristics of the comparison distribution. So we need to know things about this null distribution that we're going to compare our observed result to, which we'll refer to as the comparison distribution. So again, the comparison distribution is the null distribution. So in our example, the characteristics of the comparison distribution are known exactly. It's a normal distribution with a mean of 14 and a standard deviation of 3. And if we convert the scores in this null distribution to z-scores, it's a standard normal distribution with a mean of 0 and a standard deviation of 1. Because remember, all standard normal distributions have these parameters. Step 3 is determining the cutoff score for rejecting the null hypothesis. So in step 3, the question of interest is, how extreme does our observed result need to be in order for us to conclude that the vitamin had some effect? So remember that extreme can mean very high or very low, depending on the specific research hypothesis. In this instance, we care about an extremely low result because the research hypothesis states that babies who get the vitamin will walk sooner, or in other words, a lower number of months. So we'll cover this in more detail when we discuss one-tailed and two-tailed tests next lecture. Now, what counts as extreme enough is ultimately somewhat arbitrary. There is no magic number, simply what is agreed upon by researchers in a given field. So if we're using a significance level of 0.05, which is standard in social sciences, this step requires that we find the z-score, or the score in general, that isolates 5% of the area under the curve in its tail. So from the table in the appendix, we find whatever positive z-score isolates 5% in the tail of the distribution, and we make this number negative, and that will be your cutoff value. Now from the Shiny app, we adjust the probability to 0.05, and we choose a one-tailed lower test, testing for the presence of an extreme negative result. And we obtain a z from the top of the graph. Both of these should get you the same answer, which is z equals negative 1.64. So a z of negative 1.64 always isolates 5% in the tail. So thus, if our sample z-score is lower than this, negative 1.64, then we'll reject the null hypothesis. So once steps 1 through 3 are in place, you need to actually calculate the test statistic in question based on your observed data. And we're going to use the z-score here again as our test statistic. And we collected data from an n equals 1, so one baby who took this vitamin and started walking at 8 months. So our x, or score, is 8. So how extreme is the score of 8 in reference to the comparison distribution, so that null distribution, the general distribution of non-vitamin babies? So let's calculate that z-score. So our score, 8 minus the mean of that null distribution, which is 14, divided by the standard deviation of that null distribution, which is 3. So our z-score is negative 2. So now we'll simply determine whether our result of z equals negative 2 is extreme enough to reject this null hypothesis. There are two ways you can do this. So from your test statistic, or z equals negative 2, you can compare that test statistic calculated from your sample to the cutoff value you determined in step 3. So if your sample is more extreme in the positive or negative direction, depending on the hypothesis being tested, then this cutoff value, you reject the null. Or you can do it directly from the p-value. So determine the probability of finding the test statistic that you did, so in this case, negative 2. And this would be called the p-value. So I think earlier we calculated this as being 0.02. And if this p-value is lower than 0.05, you reject the null. So in this case, it is, because 0.02, the p-value that we calculated earlier on the Shiny app, is lower than 0.05, which is our p-value cutoff, or the significance level we chose before running the experiment. Therefore, we can reject the null. So if our z-score is more extreme than the cutoff z-score of negative 1.64, it is, so we reject the null. If our p-value, the probability of finding a test statistic as or more extreme than ours, assuming the null is true, is less than 0.05, you could use the Shiny app or the table to find this p-value. And for a z-score of 2, we got p equals 0.023. So yes, that is smaller than 0.5, so we reject the null. So these are simply two different ways of getting the same piece of information. And they'll always agree in their conclusions, assuming that we don't make any mistakes in our calculations. Here are a few things that are important to remember. If we have two pairs of z-scores and p-values, like we do here, the extreme enough cutoffs and the actual results we obtain are important. So cutoffs for a standard normal distribution, our cutoff levels will be z equals plus and minus 1.64, which equates to a p equals 0.05, or the probability of scoring as or more extreme than this. And then we compare these to our observed results, which is a z equals -2, which is associated with a p equals 0.023. The probability of scoring as or more extreme than this value. So you need to compare this to this in order to determine whether or not you can reject the null hypothesis. All right, so always note that we have two pairs of z-scores and p-values we're dealing with, the extreme enough cutoffs, and the actual results we obtain. Now, proper language use and interpretation is crucial. So finding a p less than 0.05 does not prove the research hypothesis or imply that it is true. Everything we're doing is based on probability. So results can suggest or support a hypothesis, and there are different ways to gauge the strength of the support, but not prove the truth of any given hypothesis. Now, finding a p-value greater than or equal to 0.05 does not mean that the null is true. It simply means that we can't reject the null based on our findings, because our result would likely be likely if the null is true, right? So a high p-value means that our result is more likely under this null hypothesis. Therefore, we can't reject the null. Now, NHST does not allow you to make probabilistic statements about the null hypothesis. So you can't say, this null is likely to be true given our results. No, you can only really say things about a p less than 0.05. So to sum this up, finding a p-value less than 0.05 does not prove your research hypothesis or imply it's true. And finding a p-value greater than or equal to 0.05 does not mean that the null is true. And you can't even say that finding a p-value greater than 0.05 supports the null hypothesis. So if you find a p equals less than 0.05, your findings are statistically significant. Your research hypothesis was supported. You can reject the null hypothesis, and you can say that there is a difference between groups or a relationship between variables x and y. And finding a p greater than or equal to 0.05, you can say that your results are not statistically significant, usually labeled non-significant or NS. You can say that you failed to reject the null hypothesis, and that results are inconclusive. So a table in the textbook which breaks this down. You can pause and take a look at that. In next class, we're going to touch upon some current debates surrounding the heavy reliance on NHST and p-values in psychological science and social sciences more broadly. Psychology is a field within social science which is currently being ridiculed to some extent for replication issues, which stem from the use of NHST and p-values. And I'd like to leave you all with a in-class problem for you to work through, similar to what we did with the vitamin baby example. So a researcher has developed a memory training technique and decides to test out this on one of his students. And the student undergoes the memory training procedure and then takes a memory test and scores a 13 out of 20 points. Now let's assume that the distribution of the test performance in the general population of students has a mean of 9 and a standard deviation of 3. So that again is our null hypothesis distribution. And I want you to answer the following. What is the z-score for the student who underwent the memory training using these three pieces of information. What is the p-value for this z-score in a one-tailed test? And based on this, should the researcher conclude that the training worked? Why or why not? Using a significance level or a p-value cutoff of 0.05. Well, thank you very much and have a good weekend.